Hello, my name is Vishnupriya Radhakrishnan, and I will be presenting the top 5 manufacturing processes that we've covered in class. In this presentation, I'll be going over abrasive water jet machining, electrical discharge machining, incremental forming, precision forging, and laser beam machining. The purpose of this presentation is to discuss 5 very important manufacturing processes and cover how they work, their applications, and why they're vital in modern manufacturing. First, let's talk about abrasive water jet machining. Abrasive water jet machining uses a high-velocity water jet mixed with abrasive particles to erode and cut materials. This method is cold, meaning it doesn't generate heat that could affect material properties. It's known for its precision and is used in sectors like aerospace, while cutting composites without thermal stress, automotive, where we're creating custom parts, and construction, while cutting brittle or flexible materials like stone and glass. The jet nozzle directs the water and abrasives at high pressures up to 60,000 psi, cutting through tough materials without any heat-affected zones. Since it's a cold cutting process, abrasive water jet machining doesn't introduce heat into the material, which preserves the integrity of sensitive materials. Plus, it produces minimal waste, making it a sustainable option. Some of the capabilities include precise cuts, flexibility to create intricate shapes without requiring starter holes, save for heat-sensitive materials. And some limitations are it's slower than laser or plasma cutting for thicker metals. It requires high water and power usage and may be less effective on certain metals. Next, let's talk about electrical discharge machining, or EDM. EDM removes material through high-frequency electrical discharges. This method is particularly suited for machining hard, conductive materials like tools, steels, and superalloys, and is known for achieving tight tolerances. EDM is invaluable in mold making, aerospace, and precision tooling. It's used for parts requiring intricate shapes or high tolerance, such as injection molds and turbine blades. During EDM, a spark is generated between the electrode and the workpiece, eroding material in precise locations. It allows for detailed, complex geometries that would be impossible or inefficient with other methods. It can create tiny cavities or thin walls without exerting physical force, reducing risks of deformation. Its ability to machine very hard materials and produce intricate details makes it crucial in high-tech fields. Some benefits include high accuracy, no physical contact with the workpiece, works on very hard materials, and some limitations are it's a slow process, it's high in cost, and it's limited to conductive materials. Incremental forming. This process gradually shapes a workpiece through repeated small movements. This allows complex geometries to be formed without expensive dedicated dies, making it ideal for custom parts and prototyping. This process is widely used for prototyping in the automotive industry, for custom parts, and the medical industry for personalized implants. The process is generally a tool that incrementally deforms the material in small steps, progressively creating the desired shape. Since incremental forming requires minimal tooling, it's more affordable than other methods for small batches. The process's flexibility also enables complex shapes, enhancing its appeal for custom or prototype parts. Some benefits include it's great for complex shapes and prototypes, adaptable to many shapes, cost effective for small runs. Some limitations are it's slow and less precise than traditional forming methods, limited to certain materials like aluminum and softer metals. Next, let's talk about precision forging. Precision forging shapes metals with high accuracy by compressing them in custom designed dies. The result is near net shapes with minimal need for further machining. It's favored for high strength, high precision components. Some applications are it's used for parts requiring durability and precision, such as automotive gears, aerospace components, specifically turbine blades, and heavy machinery parts. The precision forging involves compressing heated metal in a die cavity, ensuring high accuracy and strength. Dies are custom designed for each part to achieve precise dimensions. Precision forging combines high strength with dimensional accuracy. It minimizes waste, aligning well with cost effective and environmentally conscious manufacturing practices. Some benefits are it's high in precision, reduces waste, strong and durable parts, and is suitable for high stress applications. Some disadvantages include expensive initial tooling cost, limited to high strength materials, and requires specialized equipment. The final topic is laser beam machining. An overview of this process is it employs focused laser beams for precise material removal or surface finishing. This non contact process prevents distortion, making it ideal for delicate materials. It's popular in electronics, medical device manufacturing, and automotive. A laser beam is essentially directed at the workpiece, with the laser energy heating and vaporizing material at targeted points for precise cuts. Laser beam machining is invaluable in high-tech fields where cleanliness, precision, and minimal material distortion are essential. Its capacity for extremely precise cuts without physical contact or heat-affected zones is very important for sensitive materials and high precision needs. Some benefits include non contact, high precision, and minimal material wastage, and it works well on intricate shapes. And some disadvantages are its high energy consumption, and it's best for thinner materials. It has an expensive setup and limited speed for thick materials. These are the references that I used to research about every process. Thank you for listening.